Let's introduce some notions on vectors. The first one is that we want to define the length of a vector, say x equals x1, x2. The symbol is x with two vertical bars on each side of the vector, and it is defined as the square root of x1 squared plus x2 squared. This definition makes sense when we try to draw the vector on the real plane. The length of the vector, which is the length of the arrow drawn, is the hypotenuse of a right-angled triangle, where the other two sides are the horizontal and vertical distances of the point away from the origin. Hence, the length is given by the Pythagoras theorem. If the length of the vector x happens to be 1, we call x to be a unit vector. The second notion is the distance between two vectors, say x equals x1, x2, and y equals y1, y2. Such a distance, denoted by the length of x minus y, is the square root of bracket x1 minus x2 squared plus bracket y1 minus y2 squared. This definition follows readily from the definition of the length of the vector x minus y. The third notion that we want to define is the scalar product, which is also called the dot product of two vectors, say x and y. It is denoted by x dot y, and it is equal to x1 times y1 plus x2 times y2. In other words, we multiply the corresponding components of the two vectors and add up the results. Let's do a quick example on the three notions we have just introduced. Let's say we have the vectors x equals 1, -1 and y equals 2, -3. Then the length of x equals the square root of 1 squared plus bracket -1 squared, which equals the square root of 2. Also, the length of y is the square root of 2 squared plus bracket -3 squared, which equals the square root of 13. Also, x dot y equals 1 times 2 plus -1 times -3, which equals 5. Now, let's talk about some properties of the three notions. For any vectors x, y, and z, we have the following properties. The first one is that x dot y equals y dot x. This can be easily seen from the definition, since x1 times y1 plus x2 times y2 equals y1 times x1 plus y2 times x2. The second property is that x dot bracket y plus z equals x dot y plus x dot z. This can also be seen from the definition, since x1 times bracket y1 plus z1 plus x2 times bracket y2 plus z2 equals x1 times y1 plus x2 times y2 plus x1 times z1 plus x2 times z2. The third property is that bracket x plus y dot z equals x dot z plus y dot z, and this follows from applying both the first and the second property. The fourth property is the following. If we take the square of the length of x, it is equal to x1 squared plus x2 squared, but this by definition is x dot x, and since we have a sum of two squares, it is greater than or equal to 0, and this would be equal to 0 if and only if both x1 and x2 are equal to 0. In other words, x is the 0 vector. The fifth property is that whenever lambda is a real number, the length of lambda times x equals the absolute value of lambda times the length of x. Indeed, the length of lambda times x equals the square root of bracket lambda times x1 squared plus bracket lambda times x2 squared. We can factor out the lambda squared and get square root of lambda squared times bracket x1 squared plus x2 squared. We know that the square root of lambda squared equals the absolute value of lambda, and what's left is the square root of x1 squared plus x2 squared, which is just the length of x. The sixth property is that the absolute value of x dot y is less than or equal to the length of x times the length of y. This cannot be easily seen from the definition, and we will prove that in just a moment. The last property is that the length of x plus y is less than or equal to the length of x plus the length of y. Again, we will prove this property later in the video. So now let's prove the sixth property, which states that for any vectors x and y, we have that the absolute value of x dot y is less than or equal to the length of x times the length of y, with equality if and only if x equals lambda times y for some real number lambda. This is known as the Cauchy-Schwarz inequality. To prove this, first we observe that if x or y is equal to the zero vector, then x dot y is equal to 0, and also the length of x or the length of y is equal to 0. So both sides of the inequality are 0, and so it holds trivially. So let's assume that both x and y are not the zero vector. We consider all vectors of the form x minus lambda y. We know that the length of x minus lambda y squared is greater than or equal to 0, and we can rewrite it as x minus lambda y dot itself. By using a property of the dot product, we can expand the bracket to get x dot x minus x dot bracket lambda y minus bracket lambda y dot x plus bracket lambda y dot bracket lambda y. Now, x dot x is just the length of x squared, and for the middle two terms, we can take out the common factor lambda to get minus 2 lambda times x dot y. For the last term, we get lambda squared times y dot y, which can also be written as the length of y squared. Now, observe that this is a quadratic polynomial with real coefficients. Let's call it p of lambda. Since p of lambda is greater than or equal to 0, it takes non-negative values only. This implies that p of lambda has at most one real root. That means that the discriminant of p of lambda is less than or equal to 0. By plugging in the coefficients of p of lambda, this means that bracket negative 2 times x dot y whole squared minus 4 times the length of x squared times the length of y squared is less than or equal to 0. This can be simplified to x dot y squared is less than or equal to length of x squared times length of y squared. We can take the square root on both sides to get the absolute value of x dot y is less than or equal to the length of x times the length of y. So the inequality is established. It remains to show the condition for equality. Now, we have the absolute value of x dot y equals the length of x times the length of y implies that the discriminant of p of lambda equals 0. That means that p of lambda has a repeated real root, say lambda naught. Hence, p of lambda naught, which by definition is the length of x minus lambda naught y squared, is equal to 0. Hence, the vector x minus lambda naught y equals the 0 vector. In other words, x equals lambda naught y. Conversely, suppose that x equals lambda times y for some real number lambda. Then, the absolute value of x dot y equals the absolute value of bracket lambda times y dot y. This equals the absolute value of lambda times the absolute value of y dot y. By definition, this is equal to the absolute value of lambda times the length of y squared. On the other hand, the length of x times the length of y equals the length of lambda times y times the length of y, which is equal to the absolute value of lambda times the length of y squared. Therefore, we have shown that the absolute value of x dot y is equal to the length of x times the length of y, and the proof is complete. Now let's also prove the last property. It is that for any vectors x and y, we have that the length of x plus y is less than or equal to the length of x plus the length of y. This can be easily understood by drawing out the addition of the two vectors. A triangle is formed, and so by the triangle inequality, the sum of the lengths of the two shorter sides, in other words, the length of x plus the length of y, is greater than the length of the longest side, which is the length of x plus y. However, we have an equality condition here, because for vectors, we allow that x and y are parallel. In other words, x equals lambda times y for some real number lambda. To prove this result, we observe that both sides of the inequality are non-negative, so it is equivalent to showing the inequality when both sides are squared. In other words, the length of x plus y squared is less than or equal to the square of the sum of the length of x plus the length of y. Expanding, we get the length of x squared plus 2 times the length of x times the length of y plus the length of y squared. Now, the left-hand side, the length of x plus y squared, can be written as x plus y dot itself, which again, by the properties of the dot product, it is equal to the length of x squared plus 2 times x dot y plus the length of y squared. By the previous proposition, which is the Cauchy-Schwarz inequality, we get that x dot y is less than or equal to the length of x times the length of y, with equality if and only if x equals lambda times y for some real number lambda. This proves the result. Let's prove one more proposition, which gives a useful expression for the dot product. It states that for any vectors x and y, x dot y equals the length of x times the length of y times the cosine of theta, where theta is the angle between x and y. The proof of this result is based on a triangle where the three sides are formed by x, y, and x minus y, respectively. Applying the cosine law, we have that the length of x minus y squared equals the length of x squared plus the length of y squared minus 2 times the length of x times the length of y times the cosine of theta. On the other hand, the length of x minus y squared equals x minus y dot itself, which again, by the properties of the dot product, it can be written as the length of x squared minus 2 times x dot y plus the length of y squared. Comparing the two expressions, we get that x dot y equals the length of x times the length of y times the cosine of theta, and this proves the result. Observe that this expression for the dot product gives us a condition for when two vectors are perpendicular. Indeed, the two vectors x and y are perpendicular if and only if the angle between x and y, which is theta, is pi over 2, or 90 degrees. In this case, the cosine of theta equals 0, so from the above expression, it means that x dot y equals 0. In other words, x dot y equals 0 is a condition for when x and y are perpendicular. Let's end this video with the following definition. If we have a vector which is perpendicular to a direction vector of a line L, then the vector is called a normal vector to the line L. More precisely, if L is the line u plus lambda v, where v is a real number, and v is v1, v2, then the vector defined by n equals negative v2, v1 is a normal vector to L. Indeed, by using the previous expression of the dot product, it suffices to show that v dot n equals 0. By definition, v dot n equals v1 times negative v2 plus v2 times v1, which is indeed equal to 0. Hence, we have shown that v and n are perpendicular, so n is a normal vector to L.